In a perfect world, we'd be able to find the time complexity of a divide-and-conquer algorithm easily. We don't live in that world. But we might be able to find the time complexity of one step of the algorithm, then use it to find the overall time complexity. So let's take a look at Horner's method again. In Horner's method, we split a kth degree polynomial into a constant term and x times a k minus first degree polynomial. To compute this, we'd need some number of steps to compute the k minus first degree polynomial, one multiplication, and one addition. So computing a polynomial of degree k requires pk minus 1 plus 2 steps. This is an example of a recurrence relation. It describes the next value in terms of an earlier value or values. Recurrence relations are generally easy to find, but they're hard to use. For example, let's try to find P5 where Pk is Pk minus 1 plus 2, and P1 is 2. So we know that P5, well, that's P4 plus 2. But we have P4, well, that's P3 plus 2. And P3 is P2 plus 2. And P2 is P1 plus 2. And we finally know what P1 is, so we can substitute that in, and we find. Now, while we can use the recurrence relationship this way, what we really want is the closed form expression for the terms of the recurrence sequence, a simple formula that allows us to compute the kth term directly. It's generally easy to find a recurrence relation. It's generally very hard to find a closed form expression for it. To find that closed form, we need the recurrence relation, the starting value or values, and insight and creativity. So for example, let's find a closed form expression for this where P1 equals 2. So remember, concrete never hurts. Note that when we found P5 earlier, we ended with a sum of 2's, and notice that the number of 2's was the same as the index. And this suggests Pn is 2n. It's important to remember, no computer ever lost its job for making a mistake. And what this means is we should prove that the terms of the recurrence relation, where P1 is 2, are in fact given by 2n. And we note that this is an ordered sequence of claims. P1 is 2 times 1, P2 is 2 times 2, P3 is 2 times 3, and so on. So we'll use induction. Now, the base step, P1 is 2 times 1. This is true since P1 is in fact 2. For the induction step, we want to prove that if Pk is 2k, then Pk plus 1 is 2k plus 1. So remember, you can always assume the antecedent. You can always assume the if part of the statement. So suppose Pk is 2k. The recurrence relation tells us that Pk plus 1 is Pk plus 2. We assume that Pk is 2k, so we could replace that. And let's see, I want to get to 2k plus, oh, well, if I just factor a 2 out, I get what I want. And so if Pk is 2k plus 1, then Pk plus 1 is 2 times k plus 1. So the claim is true for n equals 1, and if the claim is true for n equals k, then it's true for n equals k plus 1, and consequently we may conclude that Pn is in fact 2 times n.